Hello and welcome to this lecture on decoding LDPC codes. So far we have seen the definition of the parity check matrix for LDPC codes in the 5G standard. We saw how to encode them. We even wrote a small MATLAB program for encoding these codes. So all that is ready. Now we are ready to jump into decoding. Okay, so how do we decode? The decoder is at the heart of the success of LDPC codes, like I have mentioned before. It is a message passing iterative decoder. It works in multiple rounds of iterations and it actually consists of reasonably simple operations, and the memory structure is what is important. So you have to store a lot of things in memory and move it around, access it, etc. Okay, so you will see as we describe the decoder what is involved. The principles are interesting and simple. Once again, we will not look at too much of the theory. We will focus on the implementation aspects. Some of the things I do will be repetitive in the sense that you will be reminded a lot of the single parity check decoding because the single parity check is an important ingredient in the decoder for LDPC codes. Okay, so let us get started. As a quick overview of where we are with respect to LDPC codes. LDPC codes are linear codes specified by a sparse parity check matrix. Most of the entries are zeros, so very few ones. It was proposed long back in the 60s. Since the 90s there has been a revival in these codes, and now they are a part of many standards, earlier standards too, and now the 5G standard also has them for the data communications part. Okay. So what are the main points to note? The decoder for LDPC codes is soft input, soft output. Okay, so you remember the soft input, soft output decoders I spoke to you about. You deal with these beliefs or log likelihood ratios for the received values and for the bits in the code word, and then you improve them using some calculation. It is iterative in the sense that it does not try to decode the entire code at once. Okay, so it will use some partial information from the code and then do some decoding and then pass messages around. Okay, so that is sort of the idea in this. There is an approximation involved which is called the min-sum approximation. We have spoken about it. This is a very well studied decoder today. Okay, so many papers are there in the literature. We will not look at an exhaustive study of all possible variations, just one type of decoding which is quite popular in practice today. Okay, that is how we will proceed. Okay, so the setting is sort of similar to how we have been doing all along. You have BPSK over AWGN, the noise standard deviation is sigma. The code word is C1 to Cn. Okay, so you have the code word here which is C1 to Cn. So each Ci is okay. So this is the code word and each Ci is a bit, okay, 0 or a 1. Okay, this is a bit. This is the received value. Remember, this is Ci first gets converted into Si, which is the BPSK modulation. Okay, you can see the BPSK modulation here. 0 goes to +1, 1 goes to -1. Okay, it gets converted into a symbol, and then this is the received value. Okay, real value. Okay. So now a lot of you might know, if you have some implementation background, the real values are not really used in its entirety. In the decoder, you always quantize it to say 5 bits or 6 bits or 7 bits. I will mention that later on, but for now we will keep it as the real value R as far as the description of the decoder is concerned. Eventually these will all be integer values after suitable scaling and quantization. Okay, so that will happen later on. Okay, so this is the received value. We talked about this LLR, which is the channel LLR. Okay. Is log of this ratio of probability of Ci given the particular bit, okay, particular received value Ri alone, and that becomes this assuming you know Ci is uniform. Okay, then you have this, and for BPSK over AWGN you have this very simple formula for the LLR, right. So we saw this before, 2 times Ri by sigma squared is the channel log likelihood ratio for the particular received value. Okay. Given Ri alone, the belief on the bit is 2 Ri by sigma square. So it is proportional to 2 by sigma square, and you can see this is important to know. Okay. Proportional to Ri, I am sorry, Li is proportional to Ri, and the constant is 2 by sigma squared. So this part is either needs estimation or usually can be ignored. You can just simply set it as 1 in your decoder. Okay, so we will do that later on. So, what we seek is the output LLR, where here you have the entire received vector. Okay, given the entire received vector, what can I say about the probability of a particular bit being 0 or a 1? Okay. Now, it turns out if you want to exactly write down an expression for this, it is possible, but the complexity is really huge. You have exponential complexity in k and n and all that, and particularly if k is 1000, n is 2000, you have no hope of doing it. Okay. So, what will happen in this decoder is we will approximately iteratively compute this. Okay. Not compute exactly, of course, of approximate computation, but we will iteratively go towards it. We will slowly improve the log likelihood ratio using more and more information from the remaining code words, right. So, this Li, small li uses only information from Ri. We will try to use other bits information slowly in a iterative manner and expand the belief that you have, I mean, make the better belief that you have on the bit better and better. Okay. So, that is the sort of philosophy. We will be a little loose on describing that going forward. Okay. So, let me describe what happens a little bit more clearly. So, let us focus on the low density parity check matrix. So, this is the matrix. Okay. This is only a part of the matrix, the top left, if you will. Okay. So, the first column has 3 ones. Okay. So, the first column has 3 ones, everything else is 0, and the ones are in the first row, 5th row and the 9th row. Okay. Every other row has 0 in the first column. Okay. There is 1 only in the first row, 5th row and 9th row. Okay. And if you focus on the first row has 1s in the 4th column, 8th column, 12th column. Of course, the first column is also a 1. 4th, 8th and 12th column. Likewise, the 5th row has 1s in the 2nd column and 10th column and 20th column. Okay. And the 9th row has 1s in the 6th column, 16th column and 18th column. Okay. Remember, this is a sparse matrix. So, you expect a lot of zeros. Okay. There will be a lot of zeros, very few ones. Okay. So, this is the one. This is sort of the local structure. So, this notion of a local structure is very important in this approximate iterative message passing decoders. If you just focus on the first bit alone and look at the parity check matrix, this is how everything looks. Okay. You do not see anything more beyond this. Of course, the first bit is also affected by other bits. These are not the only bits which affect the first bit, right, because through these bits it is further connected to other bits, right. The 12th column may have more ones. Okay, and then that might have more connections. Okay, all of that is there, but for now we can ignore all of that and just focus on the immediate structure in the first bit. Okay. Now, if we are given only R1, okay, we know what the belief of the first bit is. This is like the first estimate. Okay, so, this is only from channel. Okay, you are given only R1, what can you say about the belief of the first bit? 2R1 by sigma square. So, that we know, there is no problem. Okay. So, what we do now is we try to exploit the local structure, okay, the connections in row 1, row 5 and row 9. Okay. Now, what does row 1 tell you? Okay, we saw this before. Every row of the parity check matrix actually defines a single parity check code. It gives you a parity check constraint that is satisfied by one subset of the bits of the code word. So, row 1 is telling you that C1, C4, C8 and C12 belong to the single parity check code. Okay. So, that is something that we know. Okay. So, using just the SPC decoder, okay, so the second estimate is formed by the single parity check decoder. You can compute another estimate for the first bit, okay, the log likelihood ratio of that bit given R4, R8 and R12. Okay. So, how will I do this? I can do the min sum approximation or even the exact computation with the log tan hyperbolic function, etc. You can compute the extrinsic estimate from this. Okay. So, this should again be extrinsic. Okay. So, this is easy enough to do. I am using only the single parity check code defined by the first row. It is the same way row 5 also defines a single parity check code involving C1, C2, C10 and C20. So, now I can use the same single parity check code again, but with R2 and R10 and R20. Okay. Now, I will get another estimate, okay. That is again extrinsic, again uses a single parity check decoder, the same structure again, but with different received values, okay. Now, you get another estimate, third estimate, okay. So, likewise you can also form a fourth estimate, okay. So, which comes from row 9, which is C1, C6, C16 and C18. So, the local structure has given you already 4 estimates, okay. The first estimate came from the channel itself, second estimate came from the first parity check it was in the bit was involved in, third estimate from the second parity check, fourth estimate from the third parity check. So, every parity check in the local structure gives you more estimates for that particular bit. And how were those estimates calculated? Using the single parity check decoder, the soft in soft out decoder, okay, and you compute the extrinsic information, okay. So, the same thing can be done for every other bit as well. Is that okay? So, I showed you for the first bit. Now, even if you go to the 200th bit, the 200th bit will have a local structure. It will have certain ones in the columns which are connected to certain ones on the rows. You can go and do the same computation, okay, except that you should know which bits the 200th bit is connected to, which are the rows, where are the ones. Once you know where the ones are, you can go pull out these received values, send them through the same SPC decoder. So, you just need this single parity check decoder which will keep doing CISO calculations for you, okay. So, that is the trick to this, okay. So, that is the essential ingredient in an LDPC code. So, you use the local structure and get more estimates for a particular bit, okay. Now, this is not the whole story, okay. So, only the local structure only conveys partial information, right. So, you are not still connected to the rest of the code words, rest of the bits in the code word or the received values. Only the first 20 or so received values are being used here, okay. In fact, not even 20, 3, 6, 9, 9 other received values are being used here. This code might be 2000 bits long, okay. So, then you have to use the other received values as well, but you want to do it efficiently. For that you use message passing, okay. So, each code will use the local structure and then pass messages to each other and improve each other in some iterative nice fashion, okay. So, that is the essential idea, but this vision of how the code works through the local structure row wise is very important in implementing and also understanding how the decoder works, okay. So, we will see some more concrete examples going forward, but this is the setting, okay. Okay, so how do you calculate this? We have seen this before, so I am going to go through this really fast without spending too much time on it. We saw that if you have two binary random variables x, y, this is the modulo 2 addition, okay, and z is x plus y, then this is true, okay. 1 minus 2z is 1 minus 2x into 1 minus 2y. This is the same as XOR. Okay, so, if you do not believe me, you can make a little table here, x 1 minus 2x, y 1 minus 2y. If you look at it, maybe I should write it a bit more with some more space. So, if you make a little table here, or maybe I can go to the, yeah. So, if you make a little table here, x, y, z equals x XOR y, say 0 1 0 0, I am sorry, 0 0 0 1 1 0 1 1, you have 0 1 1 0. If you look at 1 minus 2x, 1 minus 2y and 1 minus 2z, do like the BPSK modulation, so to speak, you have 1 1 minus 1 minus 1, 1 minus 1 1 minus 1, and if you look at 1 minus 2z, you get 1 minus 1 minus 1 1, and which is actually equal to 1 minus 2x times 1 minus 2y. Okay, you can multiply these two and you get this. Okay. So, this is sort of after BPSK the XOR becomes multiplication, okay. In terms of plus 1 minus 1, it is a multiplication. Okay. So, that is what is being used here, 1 minus 2z is 1 minus 2x into 1 minus 2y. Now, you can take expectations. Okay. You can take expectations. These binary random variables we will assume are independent or at least uncorrelated for this purpose. So, if you take expectation, expected value of a binary random variable being equal to 1 is the same as probability that it is equal to 1. Okay. So, that is another little quick little result that one can derive. So, remember if x is 0 or 1, this is p of 0, p of 1, expected value of x is 0 times p of 0 plus 1 times p of 1, and that is just p of 1. So, for a binary random variable, expected value is equal to the probability it takes the value 1. So, if you take expectations, it just becomes this product. Okay. Now, you can do this little bit of work here and define this Lx to be log Px of 0 by Px of 1, okay, and likewise for Ly and Lz also, and you can show that this is true. So, this is a result I showed earlier on with tan hyperbolic. Okay. This is the crucial result here. Tan hyperbolic of Lz by 2 is tan hyperbolic of Lx by 2 times tan hyperbolic of Ly by 2, and then you use the fact that it is an odd function and separate it into sign and absolute value, and when you extend z to x1 plus x2 plus x3 plus xw, the same thing applies. Okay. The signs multiply for Lz, absolute value works through this function f. Okay. So, we have seen all this before. I am just doing a quick recap to tell you why the SPC SISO decoder is easy to compute. That is the main thing here. Okay. So, one can do a good implementation of this. It is possible to do it in hardware quite efficiently. Okay. So, nevertheless, people tend to approximate this. So, there is a useful reason why you want to approximate it. It is good to have further lesser computations, and if it is good enough, if it is close enough to actual the exact computation, why do all that? So, most people do this min sum approximation. I have called it minimum approximation. So, let us just say min sum approximation, which is the best thing to do here. So, we saw this before. So, the absolute value is dominated by the minimum of these values. Okay. So, it saves the computation of a nonlinear function. There is really almost no loss in practice. So, usually one can do a little offset as well. Okay. So, this is also something we have seen before, and we will use it in the decoder. Okay. So, like I said, this is actually the Tanner graph corresponding to the parity check matrix we saw before. Okay. In the earlier slide. Okay. So, let me show you that earlier slide real quick. Okay. So, this is the parity check matrix. You have row 1 connected to column 1, column 4, column 8 and column 12. Okay. So, if you go back to the Tanner graph, you have bit node 1 connected to check node 1, check node 5 and check node 8. Okay. So, this computation, this local structure computation is very conveniently captured in the Tanner graph. Okay. And what does the Tanner graph further capture? It further captures the message passing through which these bits exchange the local structure information without leading to any problems. It captures all of that very nicely. Okay. So, if you look at the first iteration, okay, where you obtain these estimates, okay, this Li is passed from bit node I to check node for all the bits. Okay. So, instead of just talking about the first bit, I can now talk about all the bit nodes. Now, all the bit nodes will be passing the LLR to all the check nodes that they are connected to, and all the check nodes will do the SPC decoder computation. Okay. So, the check nodes will do SPC SISO computation. Okay. So, in the first iteration, you can imagine the channel received value comes into the bit nodes, you do the LLR channel LLR calculation 2 by sigma square Ri, and then that LLR gets passed to all the check nodes on the Tanner graph. Okay. So, the Tanner graph nicely captures this passing of messages, and then what does the check node do? Check node does single parity check SISO computation. Okay. And then it passes back the extrinsic on each of the edges back to the bit nodes. Okay. So, that is how you get this L11, L15, L19. Okay. So, how exactly does this happen? So, let us look at it very closely here. Okay. So, let me show how that happens very slowly. So, you have the check node 1 which is connected to bit node 1, bit node 4, bit node 8 and bit node 12. Okay. So, the message or LLR that comes from bit node 1 I will denote as M11, bit node 4 is M41, bit node 8 is M81 and bit node 12 is M121. These are the 4 LLRs that are coming in. Okay. Now, this check node 1 does, like I said, SPC SISO. Okay, it does the calculation, it uses the 4 guys and computes L11. Okay, and so now you have to just repeat the computation throughout. So now this will also send an L4, okay, in this and back to this, and L8 and L12 also. Okay, so it will send back information to all the bit nodes it is connected to. So now L11 will use M41, M81 and M12. On L12 on the other hand will use M11, M41 and M81. Okay, so this is what is critical in the message passing and how it can be very nicely succinctly captured. Okay, so L11 uses M41, M81 and M12 to compute the extrinsic LLR for bit 1. What is L12 on the other hand? It uses M11, M41 and M81 and computes the extrinsic information for bit 12. Okay. So likewise in one go you can do all the computation. Okay. So now that you have done the check node SISO computation, how do you do the next iteration? How do you keep moving to the next iteration? What you do in the next iteration is very interesting. Okay. So you have on the bit node you have what comes from the channel. Okay, L1 is what comes from the channel, right. Okay. And then in the first iteration you have L11 coming from this check node, L15 coming from this check node, 5th check node, L19 coming from this check node. Okay. So what you have here is a repetition code. Okay. The same code is sort of repeated 4 times, the same bit, the same bit is repeated 4 times. It came through the channel and you got one LLR L1. It seems to be coming through the check node 1, okay, and you have a LLR for it L11. Likewise it is coming through from check node 5, it has an LLR L15 and the same bit is coming through this check node 9 with the belief L19. Okay, you are getting 4 different beliefs, they are all for the same bit. Okay. So you actually have a repetition code. So what you need to implement here is a SISO for a repetition code. Okay. So that is a very neat way in which the simple SISO decoders for the repetition code and the SPC code sort of work together. So how do you compute M11? M11 is L1 plus L15 plus L19. Remember the repetition code, you just add the LLRs. How do you compute M15 and M19 in this direction? It is given here M15 is L1 plus L11 plus L19. The other 2 guys add up. Okay. So these are all, remember you have to send only extrinsic. This is an important rule in message passing. You cannot send total beliefs. If you send total beliefs, things will go wrong. There will be too much dependency in these LLRs and you will not be doing correct operations. Okay. So you have to only send extrinsic information. So if you get something, if you get L11 from this check node 1, you do not send anything with L11 back to that guy. Okay. You only send L1 plus L15 plus L19 back to that guy. Okay. So that is what happens here. It is a very neat way in which iterations proceed. Okay. So once again, if you want to summarize, okay, there is a row iteration, okay, where all the LLRs are processed in every row. Okay. This is the same as the check node computation. Okay. Check node computation happens here. So likewise there is a column iteration which is a bit node computation. Okay. So this is a SPC SISO, this is a repetition SISO. Okay. Both of them with some approximations can be made to involve only just linear operations, either additions or minimum or something like that, which is linear in the sense no major non-linear function going on. It is a very easy thing to implement. Okay. So now what you did in one iteration, you can keep repeating again and again and again. Okay. And when you repeat again and again and again, it turns out, if you imagine a little bit, for every bit you are using information from all other received values, okay, through this message passing method. Okay. Just by using a SISO decoder for SPC codes and for repetition codes, one can keep iterating and repeating and improve the beliefs. Okay. So what we are going to see next is a couple of simple examples where this is illustrated. Okay. Just one example where you will see the parity check matrix, you will see the received vector and you will see how it goes through the iterations and how the beliefs change and how they improve. Okay. So, this will give us a focus on the implementation and will help us write MATLAB programs for these decoders. Okay. So, that will be the next lecture.